Okay, we are at chapter 22, uh, electric fields. We're going to start with 22.1, properties of electric fields. I'm going to start with a little demonstration, pretty myself up here by combing my hair. Now let's see. It picks up a few pieces of paper, not very many. Let's try it with a balloon. Let's see if I can get some with a balloon. If it's not working, it's probably because it's very, very humid. Oh, there we go. Oh, I guess I have to show it on the screen. There's one little piece of paper well, there's a couple of pieces that it picked up. You can see them on the balloon there. Now, why is it doing that? Let's see if we can continue this demonstration. And oh well, didn't quite work. It's just being held up by the chair. Why were the pieces of paper picked up? It was because of the what we call static electricity. I put a charge on the comb, and that charge picked up the pieces of paper. So there's a little demonstration to start with. Let's share the PowerPoint, and here they're just we're going to see that electricity is a very, very big part of our lives. They're showing an electric train here. But we have here, this is some demonstrations of static electricity. There's a young lady touching an electrified ball, and all her you have excess electrons going to her hair, so those electrons tend to repel each other. And you have a cat that jumped into a box of styrofoam. I should get my cats to do that. Into a box of styrofoam peanuts, and of course the peanuts stick to him. And I just showed you using the comb and using the balloon how I was able to pick up bits of paper because of static electricity. So we're familiar with these phenomena. You sometimes on a cold day, if you live in a carpeted home, you slide the you're walking across the carpet. All of a sudden, you touch a doorknob, and you get a shock from the excess charge on your body. One way to get rid of that is you touch the doorknob with a key, and the little spark will take place on the key. You feel a little flick on your fingers, but it doesn't hurt. Just some inside information there. Okay, so if you take a negatively charged rubber rod suspended by a string and bring a positively charged glass rod, that means you've stripped some electrons from it, it's going to attract the negatively charged rod. There's a force that actually makes the rubber rod move towards the glass rod. Similarly, if you take two negatively charged rubber rods, you're going to get a force also. The force is going to be a repulsion. Okay, so we got a quick lesson here. Unlike charges, you have positive charges, you have negative charges. Unlike charges attract each other, like charges repel each other. So there's one quick lesson there. So because of conservation of charge, each electron adds negative charge to the silk, and an equal positive charge is left on the glass rod. We're going to learn that charges come in quanta. They're 1.6 times 10 to the minus 19 coulombs. Let's see. Okay, and it was Robert Millikan in 1909. Robert Millikan discovered that electric charges always occur in integral multiples of fundamental amount of charge E. So the electric charge is quantized, and we call it Q. And the charge is going to be Q, and it's going to be plus or minus some number of these charges, 1.6 times 10 to the minus 19. So Q is the standard symbol used for charge as a variable. Uh, the let's see. So N is an integer. If it's an electron, it's negative E. If it's a proton, it's positive E. And then there's some particles that have no charge. They're neutrons. They're neutral. They have no charge. Okay, we have three objects brought together close to each other, two at a time. When object A and B are brought together, they repel. When objects B and C are brought together, they also repel. Which of the following are true? Objects A and C possess charges of the same sign. That seems to be the case because like charges repel. Objects A and C possess charges of opposite sign. Well, if they were opposite, they would attract. So that doesn't seem to be the case. All three objects possess charges of the same sign. Well, A and B repelled, B and C repel, so that seems like a possibility. One object is neutral. Probably not. And additional experiments must be performed to determine the signs of the charges. Okay, so we know that A and B have the same charge. We know that B and C have the same charge. We don't know whether the charge is positive or negative. So the answer is A, C, and E. A, C, and E is true in this case. And I believe that ends this little introductory section, 22.1. We'll go on with 22.2 in the next video.